This mechanical properties item gives us force versus deformation, or change in length, that is, of a tensile test specimen of a width of a 1/2 inch and a thickness of 1/2 inch. No unit on the width, but we have to assume, and it's reasonable to assume, that that would be also in inches. So it's a rectangular cross section. And we have a gauge length of 4 inches, which will turn out to figure prominently in both the numbers that we are working through, as well as the significance of some of the results. All right, so we're given these plotted points. Note we've got force versus elongation or deformation, and in this case, being a uniaxial kind of test, that force would be equal to an axial stress times the cross-sectional area, and that elongation would be equal to a strain times this gauge length. Now, if we wanted to turn it into a stress-strain curve, then we would, of course, take the forces and divide by the cross-sectional area to get to the stress, and to get strain, we would take the deformation and divide by the original length of the gauge length. Alright, so we're asked to find the proportional limit. That's the end of the linear behavior. So by eye, you come along and you line up these points, and those 4 points do tend to look like they very closely follow a straight line kind of relationship. It even looks like it passes exactly through 0 by the eye test. That will turn out to not actually be true, but it's really close. So as I'm looking at that, the first one that observably falls outside of that linear relationship is point number 5, so in between points 4 and 5. So what you would do is you take the lower one, that would be the 3.3, but that is a force, not a stress, and the proportional limit for the material is a stress. So we got to get that stress calculation done. Boom. It's an approximate answer of 66 KSI. Exact to the numbers, but approximate in terms of we don't know that that's exactly where the proportionality ends, but by eye that's a reasonable kind of approach. We would not want to go up to the next point because that clearly is past the proportional limit. Young's modulus is the stiffness of the material, and the initial Young's modulus would be in the initial elastic portion. This is your first course in this, so in the basic model, when you say Young's modulus, you're just talking about this initial portion without having to state that it's the initial portion. And so we want to get the slope of this. Now, you could take any one of these 4 points in the linear region and just use it only, delta sigma, the change in stress over the change in the strain, and you could go to 0, 0. The problem is that you'll be off a little bit in the numbers, right? And on a test, it's hard to tell that, so what I would do is instead I'd say, hey, look, just let me take a range here. And so I took the first and the fourth, 3.3 minus the 0.9 kips over the cross-sectional area. That would give us the stress level, or the change in stress. And then this other part would be the change in the strain, so 0.008 minus the 0.002, and then you've got the gauge length of 4 inches. That's where it shows up prominently. And when we use that first and fourth values, you get 32,000 KSI. If you had used, say, this number up here that was outside the proportional limit, you would have gotten about 29,000 KSI. If you use any one of these individual ones, you'll get kind of close to this 32,000. It's going to vary a little bit. It will not be identical, right? For a test situation, it's fairly reasonable to just use some of the, I would bracket it here, that first and that last, because they do by eye look like they are running pretty much in a linear kind of fashion, but I wouldn't probably want to use the 0, 0 coordinate. When we want to estimate the yield stress using a particular method and approach, well, there is no distinct yielding point here. There's a proportional limit that looks fairly well understood, but not a yield. So that's why you would use this parallel line approach. Now, 0.25% is the strain value, but we don't have strain on the curve. So we have to convert that strain into a deformation by multiplying the strain by the gauge length. That gets us the 0.01 inches, and so then we come along and draw a parallel line. Well, gee, how do you do a high quality parallel line? Well, if you got your little triangle, it is kind of easy. What you do is you line up your drawing edge, and then put another piece right here so that I can slide this back and forth to where I want it to be. And so the deformation value would be the 0.01 value that for the deformation that goes along with the method, and we draw a parallel line. And so where it intersects the stress strain data, or in this case the force deformation data, gives us the critical value by the method that we would call the yield value, and that would be about 4.4 over the cross-sectional area. We get the 88 KSI. Now, it is not common that you would have a yield stress that would happen after this peak. That's very bizarre. And on a test situation, you might note it and move on with your life because you've done it exactly correctly, but you get a weird kind of result. How it actually happened is actually a mistake on my part. I did all the whole thing, and I liked pretty much what it was, and then spontaneously I said, hey, let's just change up the numbers and make that not 2 inches, but 4 inches. That was the mistake. What I wanted was for you to have a convenient, easy to interpret number. That would have been 0.005 that you drew the parallel line, and that would have put us just before the peak. And then I thought, oh no, I want to change the numbers. And frankly, I didn't think it all the way through. Just bam, came up here, changed it to 4, and that pushed us past the peak. So kind of an academic problem, frankly just a mistake on my part. Might have caused a little confusion, but that's what you would do on a test, is say, okay, that's the process. A little weird, but that's the process. The result is weird, not the process. Right? And then to get the ultimate strength of the material, again, this is a stress value, even though we say strength. And so sigma ultimate is just a peak on the stress strain curve. Right? And so we go find what that is. That's the ultimate or peak force, the max force, divided by the cross-section area, and we get 90 KSI.